Hi all, today we are going to study about the complexity analysis for depth first and breadth first search. We already have studied about depth first and breadth first search in previous sessions. Today we'll be starting with BFS breadth first search. We'll be studying about this pseudocode, the implementation of breadth first search, and we'll try to analyze how we achieve to the time complexity and space complexity of the breadth first search. So initialization of few elements is required in the first step, initialization of a queue and the initialization of an array that keeps a record of all the nodes that have been visited. We call it visited array. Now when this initialization has been done, we call our BFS method that has a graph and a start node. Let us try to write the pseudocode for this BFS method. We have already initialized a queue. Let us call this queue as small q for simplicity. Now when the start node is being passed, we simply enqueue this into my queue. We have this queue where we keep track of all the elements. Let us say I have this graph 0, 1, 2 and 3. This is my tree. Tree is also a graph. I have taken a very simple example of a graph. So whenever here 0 is my start element, so I have simply enqueued 0 to my queue. Let us write enqueued 0. Also I need a visited array. Okay, let us start with the while loop, which is actually iterating on all the element present in the array. If the queue is not empty, it checks. It keeps on iterating until my queue is not empty, is filled. If my queue is not empty, simply dequeue. So dequeue will remove the topmost element from my queue. So it will actually remove this 0 that we have already inserted. Let us remove 0. So 0 has been removed. The element that has been removed, let us call it V. I have marked V as visited, and now what we want is iterate over all the adjacent nodes U to V. In my case 0 has two nodes connected via two edges, 1 and 2. Now let us iterate over this. If my node U is not visited, then only I can add this element to my queue. So ends my for loop. Okay, previously we saw that I had 0 as my start element, 1. Now I go to 1 and 2. I see that 1 is not visited yet, so we simply enqueue 1. Okay, let's add 1. Similarly, when we travel, this for loop goes to 2, we see that 2 is also not traversed, so simply enqueue 2. Great. The while loop is still true, so it will again go iterating. It will again dequeue. This 1 will be dequeued. All the adjacent nodes to 1 will be added to the queue. Since there is no element, nothing is added to the queue. 1 is marked as visited. This is 0, this is 1, this is 2. So I have marked 1 as true, visited. Now this for loop is complete. Now in my queue there is just one element, that is 2. Now let us visit 2. So I simply dequeue 2. 2 is dequeued. I mark 2 as visited, done. I iterate over all the vertices adjacent to 2, so 0 and 3 are adjacent to 2. 0 is already visited, so we can't enqueue this. 3 is not visited, so let us enqueue this. 3 is enqueued. Great. Queue is not empty, again dequeue it. We dequeue 3. Let us try to see. Let us mark 3 as visited, and let us see if 3 has any adjacent vertex that are not visited. There are no vertex that are not visited, so we are done. There is nothing in the queue. Queue is now empty. It would exit the for loop, and we have completed this breadth first search. Let's talk about the complexity analysis. So first let's talk about the time complexity. So time complexity is, let's go by step. So this first step would take O of 1 time. Now comes this while loop. Let us try to find what is the time complexity for this while loop. Also we see that this is a dequeue operation, would take O of 1 time complexity. This marking visited would take O of 1 time complexity, or you can call it constant time complexity. Then we have this for loop. We also need to identify how many times this for looping node was here. 0. It executed for 1 plus 1, or in fact I should write it C for constant. So it executed for C plus, or for 0 we had 2 edges, 1 and 2, so it executed for 2 times. So we can write it over here E0. E0 is number of edges connected to 0. When the node was 1, it executed for C plus E of 1. E of 1 is number of edges connected to 1. Here it executed for 1 time, because node 1 has only 1 edge connected to it. Now let's talk about 2. So for edge node 2, it has 2 edges. Now it executed for 2 times. Let us write it C plus E of 2. E of 2 is 2 over here because it has 2 edges. Now let's talk about 3. For 3, it executed for 1 time because 3 just has 1 edge connected to it. So let us write it E3 is equal to 1. Number of edges connected to 3 is 1. So this is what we have. Similarly, it had V steps. It would be C plus E of V. When we try to sum all this, what we get is VC. V is number of vertex, and E0 plus E1, E2 till E of V. Or we can write it the number of edges connected to each vertex. We can write it summation of E of I and VC. Roughly we can write it V plus E. So I'm writing summation of E of I, summation E of I equal to E. So this is time complexity for DFS is V plus E. Talk about the space complexity for breadth first search. So we see that we have a queue that can take almost V elements. V is number of vertex. Then we have visited array that can have maximum V elements, number of vertex. Then we have the adjacency list. Now the graph representation of could be done in many ways. You could use a adjacency list. You could use a adjacency matrix. I have used over here is adjacency list. adjacency list is simply a list, an array of vertices. Let us say this is vertex 0, this is vertex 1, this is vertex 3. It has a linked list that shows number of edges connected to 0, shows number of edges connected to 1, shows number of edges connected to 2, shows number of edges connected to 3. So this is E0, this is E1, this is E2, this is E3. If we see, the space required for this array is V, number of vertices, and the space required for this is E. So the space required for adjacency list is V plus E. So we can write it V plus E. So we get 3V plus E. So space complexity becomes V plus E. So thank you for joining.